Hey guys, this is Jadhav. I'm a student at IIT Kharagpur. In this video, we are going to discuss more about gravitational potential energy. So in the last video, we have discussed the definition and we have derived an expression for the gravitational potential energy for two particle system. Now in this video, we are going to discuss more about gravitational potential energy. That is, we are going to discuss about change in potential energy for more than two particle system. So if you haven't watched my last video, I have given the link in the description. Please go and watch first, then you will understand what we are discussing now. So the expression that we derived in the last video is minus G m1 m2 by r. Okay. This is the expression that we derived in the last video. So it is the gravitational potential of m2 at a distance when it is placed at a distance of r from the source mass m1. Okay, if you consider m1 as a source mass and when you fix it, and when this m2 is brought from the infinity and placed at a distance of r, then this expression gives the potential energy of m2 in the presence of this source mass m1, or we can say this is the change in potential energy for the two particles m1 and m2 when they are brought from the lost distances and kept at a distance of r from each other. Okay, so this is the change in potential energy for the two particles m1 and m2 when they are brought from lost distances and kept apart at a distance of r. Now, what if I have n particles? How to calculate the total change in potential energy for the n particles? Okay. Now consider I have n particles. N particles like this. Okay. We have n particles. Now how can we calculate gravitational potential, change in gravitational potential energy for these n particles? If we have just two particles, m1 and m2, and when they are placed at a distance of r, then we have the expression minus G m1 m2 by r, right? But how can we find in this case? That is simple. What we do is, first we have to find the total number of possible pairs. Okay? Because we have this equation for pair, right? m1 m2 is one pair. So for this pair we have this expression. So in this case we have to find all the possible pairs, and then we have to calculate change in potential energy for the each pair, and then we have to add them to get total change in potential energy for this n particle system. Okay, maybe like this. This is one pair, 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 this is one pair. Like this we have to find all the total number of possible pairs, and we have to calculate change in potential energy for each pair. Okay, and then we have to add all these pairs, total change, we have to add change in potential energy for all these pairs to get total change in potential energy for this n particle system. Okay, so the total number of possible pairs for the n particle system are n into n minus 1 by 2. These are the number of pairs for n particles. So we can calculate change in potential energy for the each pair. Okay, we can calculate total change in potential energy for all these pairs, n into n minus 1 by 2, and then we have to add them to get total change in potential energy for this n particle system. Okay, now Let's take an example. Find the change in gravitational potential energy of three particles A, B, C having masses Ma, Mb and Mc respectively when they are brought to the vertices of a equilateral triangle of each side L from the large distances. Okay, we have to find the change in potential energy for the three particles ABC when they are brought to the vertices of a equilateral triangle from the large distances. Okay, let's consider a triangle, equilateral triangle ABC. A, B, C. Okay. Now question is, we have to find the change in potential energy when the masses Ma, Mb and Mc are brought from the large distances. Here the large distances refers to a point outside the gravitational field of some source mass, okay, or a point infinity. Now I have to bring this Ma to this point A, and I have to bring this Mb to the point B, and I have to bring this Mc to the point C. And then I have to calculate what is the total change in potential energy for this three particle system. Okay. Now for that, consider a equilateral triangle. Okay. A, B, C. First, I have to bring mass Ma from the large distance to this vertex A. Okay. First, I have to bring the mass Ma from the large distance. Okay. We consider this point as a large distance. Okay, which is far away from the triangle. Now I have to bring this Ma from this point to this vertex A. Okay. Now when I bring this particle from this point infinity to the vertex A, what is the change in potential energy? It is 0, because there are no source masses, right? When I brought this A from this point infinity to this vertex A, there were no source masses, so there is no change in potential energy, right? So the change in potential energy in bringing this Ma from the infinity to the vertex A is 0. Now I have to bring the particle Mb from the infinity to the vertex B. Okay, Mb. Now I got this Mb from infinity to the vertex B. Now what is the change in potential energy for these two particles? Right? In the first case, we don't have any source mass. But in this case, in the case of bringing this Mb, we have source mass A, right? Then the change in potential energy, change in gravitational potential energy is minus G into Ma into Mb by distance between them is L, because we said this is a triangle of having each side L, right? So this is the change in potential energy when I brought this particle Mb from the point infinity to the vertex B in the presence of Ma, right? Now I have another particle Mc. I have to bring this particle Mc from this point infinity to the vertex C. Okay. Then I have brought this to point C. Okay. Now what is the change in potential energy when I brought this particle from infinity to the vertex C? In this case, there are two source masses, A and B, right? In case of A, there were no source masses. In case of B, there was one source mass A. But in case of MC, okay, in case of bringing this MC from this point infinity to the vertex A, we have two source masses, MB and MA. Okay, so I have to calculate change in potential energy with respect to the MB, and I have to calculate change in potential energy with respect to MA as well. So the total change in potential energy for the C and B, okay, is minus G into MB source mass and then MC by distance between them is again L. And then again change in potential energy in presence of, with respect to the source mass MA is minus G into capital MA into MC by L. Right? This is the total change. This is the change in potential energy for the case when B is brought to the vertex A, brought to the vertex B in the presence of A. So this is AB. Okay. Now to calculate total change in potential energy for these three particles, I have to add all these three. Okay. I have to sum all these three to get total change in potential energy to bring these particles A, B, C from infinity to the vertices A, B, C. Okay. So then adding all these three, we will get total change in gravitational potential energy is minus G into MAMB by L, right? MAMB, and then adding plus minus G into MBMC by L plus minus G into CNA MC MA by L. Okay. This is for the pair AB, this is for the pair BC, and this is for the pair AC. So there are three pairs. So there are three change in potential energies. Okay. And adding all this, we get this. That is the total change in potential energy for these three particle system. So on taking common minus G and L, we end up with MA, MB plus MB, MC plus MC, MA. So this is the total change in gravitational potential energy for this three particle system. Okay. So you can do the same for the four particles. You can do same for the 5 or 6 or 7 or for n particles. Okay. So this is n. Thanks all.